Assalamu alaikum. Today, we want to continue talking about enzyme kinetics. And last time in part 1, we reached until slide 24. And we want to continue from here. You remember we said when we plot the initial velocity versus substrate concentration, at the beginning we have here the rate or the velocity increases linearly with substrate concentration. And we call this first order kinetics because the rate depends on the substrate concentration. However, after that, the curve levels off here, and this occurs at infinite substrate concentration, and the reaction would proceed at a maximum velocity. So here, this is known as zero order kinetics, where rate does not depend on concentration of substrate. Now remember that the concentration of the enzyme is constant, and the concentration of the substrate is much larger than the concentration of the enzyme. So now we introduce the first parameter called Vmax. Now the second one, the second parameter called Km, which is an inverse measure of the affinity of the enzyme for its substrate, so that the lower the Km value, the higher the affinity. Now, according to the steady state assumption, rate of formation of the enzyme substrate concentration equal this change in concentration of ES divided by delta T equal K1 times EFS. Now this is change in concentration of the complex during a given time, and K1 is the rate constant for the formation of the complex. Now, rate of the disappearance of the ES complex is given by the following equation. Rate of breakdown is two terms. Why? Because the ES complex breaks in two ways. One time it breaks to the left toward the enzyme and substrate, and the other time it breaks to the right toward the formation of the enzyme and the product. So we combine these two terms, and this is the rate of breakdown for the enzyme substrate complex. As you can see here, the negative sign, this one, denotes that the concentration of the complex decreases as it breaks down. Now, K inverse 1, rate constant for the dissociation of the enzyme substrate complex to regenerate the enzyme and the substrate, and to the left, and K2, rate constant for the reaction of the complex to give product and enzyme. Okay. Again, what is the steady state? It's a condition in which the concentration of the enzyme substrate complex remains constant in spite of continuous turnover. Yani, the enzyme is active, but still the rate of formation of the enzyme substrate complex equal it is rate of breakdown. So this is reached when these two rates are equal. So we equalize them like this. Delta ES divided by delta T equal minus delta. Okay. Instead of this, we put its equivalence as we saw before, and instead of this, we put these two terms. Now, substrate concentration, as I said, is much greater than the enzyme concentration. Now, when the steady state is reached, the concentration of a free enzyme is given by the following equation. This is concentration of a free enzyme equal the total concentration minus the bound enzyme. Yani the enzyme that binds to the substrate. So it is يعني بمعنى آخر the total enzyme concentration equal the free enzyme plus the bound enzyme, where E total is the total enzyme concentration. And now we substitute for E this value in the equation that I showed you here. Instead of E, we put all this and rearrange, collecting all the rate constant for the individual reactions like this. So here we have, this is called ratio of rate constant, and this is the first definition of Km. So Km, the Michaelis constant, equal to the ratio of rate constants. Okay, if you have the values of these rate constant, you can add and divide by K1 to get Km. Now, instead of all this, we put Km in the equation. And in the initial stages of the reaction, formation of product depends only on the rate of breakdown of ES. So V initial equal K2 times ES, and this equals K2 times total enzyme concentration by S divided by Km plus S. If substrate concentration is so large that the enzyme is saturated with substrate, معناته الباوند enzyme is the total enzyme, as simple as that. كمان مرة. If substrate concentration is so large that the enzyme is saturated with substrate, معناته total enzyme concentration is the enzyme substrate complex concentration, and there is no free enzyme. And V initial, the initial velocity, become the maximum velocity. When the enzyme is saturated with substrate, then V initial becomes V max. And V max equal K2 times the total enzyme concentration. Now, if we substitute for this V max in the equation, then we get the Michaelis-Menten equation. You see, this is the final version of the Michaelis-Menten equation that you should know. Don't worry about the derivation. Don't worry about the derivation, just we are interested in this. Now, again, constant rate when the enzyme is saturated with substrate is the Vmax for the enzyme. Now, if we take this equation, we plot initial velocity versus substrate concentration like this, we get a hyperbolic type of curve. As you can see here, we get a hyperbolic type of curve. Now, this red line represents the maximum velocity, which comes about when the enzyme is saturated with substrate, as I told you. Then V initial becomes V max, and you can determine this from the plot if you want. Yani. Now, we have a special condition here. And when experimental conditions are adjusted so that substrate concentration equal Km, then we substitute instead of Km in the equation S, you see, we put instead of Km S. So now V initial velocity equal 1/2 V max. In other words, when the rate of the reaction is half its maximum value, the substrate concentration is equal to the Michaelis constant. And this fact is the basis of the graphical determination of Km. So how we determine Km from the plot here, or the graph, this is Vmax, take half of it, put a line here and a line down, then you get here a value for substrate concentration. This value equals Km. So this is the second definition of Km. It's equal, Km equal substrate concentration at 1/2 Vmax. Now, if we talk about enzymes with multiple substrates, there are 3 common mechanisms. Common mechanisms for enzymes that catalyze reaction containing 2 or more substrates. One is called ordered mechanism here, where substrates have to bind to the enzyme in a specific order. Substrate first substrate first, and then second substrate, وهكذا. Random substrate can bind to the enzyme in any order. And the ping-pong mechanism, substrate binds to the enzyme and releases a product before the second substrate binds to the enzyme. And if we look at this, we will understand it more. If we look at this representation, in the ordered mechanism, you have the enzyme, then substrate 1 must bind to form EA, then substrate B binds to form this, and the reaction takes place so that the first product forms, and then the second product, Q. Now, this is called, in the random, A could bind first or B binds first. with the same results. In the ping-pong mechanism, here, the first substrate binds, then a reaction takes place, and the first product is released. طبعا here E pri is different than E, and because of the reaction. Then substrate 2 binds to E pri to form E pri B, then reaction occurs to form EQ, and the Q is released. So this is ping pong. You remember the game called ping pong like this, ping pong. Ping pong, a product must be first, often a reactant must be bound first and then the product released. Then the second substrate binds and then the second product is released and so on. Now determining Km and Vmax. Now from the plot which I showed you, it is difficult to determine Vmax experimentally. Equation for a hyperbola can be transformed into an equation for a straight line by taking the reciprocals of both sides. It's better to deal with straight lines than to deal with hyperbolas. So two scientists, one is called Lineweaver and the other is called Burke, they transformed the Michaelis-Menten equation into an equation of a straight line, into a linear equation. What they did, they took the Michaelis-Menten equation and upside it down so that we have 1 over V equal this, and then arranged it in this order so that it resembles the equation for a straight line. Now, when you plot x versus y, you get a straight line with m. M here is the slope. The slope equal Km divided by Vmax. And this is the y-intercept B. Again, this is known as the Lineweaver-Burke double reciprocal plot. Gives the slope of the line M, which equals Km divided by Vmax. Now, the y-intercept B, which equals 1 over Vmax. Then, let's look at this Lineweaver-Burke plot. We plot 1 over V versus 1 over S. We get a straight line. The slope of the line equal Km divided by Vmax. Now this y-intercept equal 1 over Vmax. And what they did is that they extrapolated this to the negative side of the x-axis. And they also found that this x-intercept from the equation equal minus 1 over Km. So here, this is a plot which is used to determine the values of both Vmax and Km. Very easily, by looking at this plot, you can determine both values. Now, the following data describe an enzyme. This is an example. This is example, and it is explained. You take this data, substrate concentration versus velocity, and he asks you plot these results using the Lineweaver-Burke plot, the one I showed you, and determine the values of Km and Vmax. So the first thing you do, you upside down these. So instead of S, we have 1 over S, instead of V, 1 over V, and then you plot these values, and you will get this straight line. You see, this straight line now has the regression equation y equals 75.46x plus 11.791. So what is the slope? The slope is equal 75.46. And this 11 here is the y-intercept. This is the y-intercept. You can take the slope which equal Km over Vmax, and you know Vmax, you know, طبعا this is 1 over Vmax. Vmax is the reciprocal, يعني. You can determine the value of Km from this equation, يعني. If I give you an equation like this, and I ask you to find the value of Km, easily you can. If you are given a plot like this, then from the plot you can determine So we said مثلا this intercept is 11. What this is 1 over Vmax. Vmax equal what? 1 divided by 11. And this one, this intercept مثلا minus 1 over Km equal minus 0.15. So Km equal 1 divided by 0.15. And the negative with the negative, they go together. And you see from the using the equation generates the following. Using this equation, we calculated the value of Km to be equal 6.39 and Vmax equal 0.0847 millimolar per second. Remember, the unit of Km is millimolar, the same as the unit for the substrate concentration. It's always like this. Now, significance of Km and Vmax. When V equal 1/2 Vmax, Km equal substrate concentration, as we did before. Consider a case in which the equation E plus S to ES takes place more frequently than ES going to E plus P, then K1 is greater than K2, K1 is larger than K2, and then Vmax is related to the turnover number of an enzyme. What is turnover number? Number of moles of substrate that react to form product per mole of enzyme per second, also called KCAT or KP. Then turnover number, also called KCAT and KP. And KCAT or the turnover number equal V divided by the total enzyme concentration. So you can determine KCAT from this. Now, what is the significance of KCAT? KCAT is a measure of the efficiency of the enzyme. The larger the KCAT, the value, the more efficient is the enzyme. You remember Km, we said, it's an inverse of the affinity of the enzyme for its substrate. The lower the Km, the higher the affinity. If you are given this table and we ask you which of these 1, 2, 3, 4 enzymes مثلا has the highest affinity for its substrate, you look at the lowest value, lysozyme. Which enzyme is the most efficient among these? You look at KCAT value, the larger value. The largest value is for catalase. So note these relationship. Don't worry about the function of each enzyme. Example of enzyme catalyzed reaction. Now, there is one enzyme called chymotrypsin. It is very well studied because it is available and simple, and what applies to the enzyme applies to many other enzymes. What it does, it catalyzes the hydrolysis of peptide bond where the carboxyl is contributed by aromatic amino acids, phenylalanine and tyrosine. In other words, chymotrypsin cleaves at the C terminal of aromatic amino acids, phenylalanine and tyrosine. So if you have a peptide bond like this, here you have R1 or R2. This is مثلا a dipeptide, and the cleavage occur here. You need water to form acid plus amine. They found also chymotrypsin in vitro often hydrolyzes an ester bond to generate an acid plus alcohol. So this is what they did in a typical reaction in which they took this ester, para-nitrophenyl ester is hydrolyzed by chymotrypsin. The experimental reaction rate depends on substrate concentration. So again, this is the example. This is para-nitrophenyl acetate in basic condition and water, para-nitrophenolate yellow plus this acetate. Now, this para-nitrophenolate yellow, so it can be followed by a spectrophotometer. So what they did now when you plot, well, I will show you the plot in a little while. Now, the other example they took, aspartate transcarbamylase. Now, this is rather an allosteric enzyme that catalyzes the early reaction in pyrimidine biosynthesis through catalyzing this reaction. Carbamyl phosphate plus aspartate to form carbamyl aspartate plus inorganic phosphate, as you can see here. Reaction catalyzed by this enzyme called aspartate transcarbamylase. They also found that reaction rate depends on substrate concentration. And let's look at the type of curves each produces. Now, the plot on the left here is a plot of reaction velocity versus substrate concentration of chymotrypsin. Now, the substrate is the para-nitrophenyl acetate. This is our ester. لاحظ, the shape is hyperbolic. So, this shape, hyperbolic for chymotrypsin when you plot velocity versus substrate concentration. However, for the other enzyme, aspartate transcarbamylase, when you plot reaction velocity versus substrate concentration, in this case, the substrate is aspartate, you get a sigmoidal type of curve. Okay, so what does this plot remind you with in protein when we talked in chapter 4? And what does this plot remind you of? Which one resemble myoglobin, oxygen binding curve, and which one resemble hemoglobin? So in chapter 4, we found that ATKs and hemoglobin are allosteric proteins, whereas chymotrypsin and myoglobin are not. This is our conclusion. Then again, chymotrypsin and myoglobin are non-allosteric proteins because they produce this hyperbolic type of curve, whereas both the enzyme aspartate transcarbamylase and hemoglobin, these two are allosteric proteins because they produce sigmoidal type of curve. And as we said for, remember hemoglobin cooperativity, hemoglobin exhibits positive cooperativity. The same is applied for the enzyme ATKs. The enzyme ATKs is an short for the whole name of the enzyme. So we call it ATKs. Okay, this is the conclusion from here. Now, let's go to talk about enzyme inhibition. Now, an inhibitor is a substance that decreases the rate of an enzyme catalyzed reaction. And there are two general types, reversible and irreversible. In the reversible here, substrates that bind to an enzyme and subsequently are released include competitive, non-competitive, and uncompetitive. Irreversible inhibitors, substances that react with enzymes to produce proteins that are not enzymatically active and from which original enzymes cannot be regenerated. Now let's start with the first type, competitive inhibition. This is the reversible type. Of the reversible types, competitive inhibition is the first one. لاحظوا, in this case, the inhibitor can bind to the active site and block the substrate site to bind to it. So we can say why there is a decrease in enzymatic activity. This is caused by binding of a substrate analog, the inhibitor, to the active site or catalytic site. So we can say that the inhibitor competes with the substrate for the active site of the enzyme and represented by two mutually exclusive equations, E plus S to form ES or E plus I to form EI. Now, an equilibrium expression can also be determined for the breakdown of the enzyme inhibitor complex, like this. Ki equal concentration of product divided by concentration of reactant. E times I divided by EI. Now, let's look at this figure also again, which is for competitive inhibition. Now the enzyme, if it binds, it can bind the substrate at the active site, okay, or it can bind the inhibitor. It is called competitive inhibition because both the inhibitor and the substrate compete for the same active site, which means that the inhibitor is a structural analog of the substrate. Now, once the inhibitor binds to the enzyme becomes inactive. The enzyme becomes inactive. They found that this type of inhibition, however, can be released by increasing substrate concentration. Now, let's see what happens in the presence of a competitive inhibitor. Now, slope of the Lineweaver-Burke plot changes. Y-intercept of the graph does not change. Vmax is unchanged. Km increases by the following factor: 1 plus I divided by Ki. We call this alpha. So Km increases by alpha. Substitute value of Km in the following equation. Okay. And you get this. So we found also that the slope increased by this factor alpha. So in a Lineweaver-Burke double reciprocal plot of 1 over V versus kada, the slope and the x-intercept change. So what changes? Both in this type of inhibition, what changes? Km increases, whereas Vmax remains unchanged. Now, what the Lineweaver-Burke plot looks like in the presence of competitive inhibitor? Let's see. You see the blue line here. This is typical, no inhibition. Again, this is the normal Lineweaver-Burke plot. And the y-intercept is 1 over Vmax, and the x-intercept equal minus 1 over Km. Now, what happens here when we add an inhibitor of this type called competitive, plus competitive inhibitor, the green one you see here, the green and the blue, they meet here, and then we have the extrapolation. What we conclude when both of them meet at the y-intercept at this point, we conclude that Vmax does not change. However, what changes is this intercept, which means that the Km value changes and it is increased. It is increased. Then Vmax no change, Km increases in competitive inhibition. In the second type, called non-competitive inhibition, form of enzyme inactivation in which a substrate binds to the site other than the active site but distorts the active site to inhibit reaction. Here, the non-competitive inhibitor is able to bind either to the free enzyme or to the bound enzyme substrate complex. وبالتالي we have this cyclic type of equilibrium, and this is why increasing the substrate concentration will not relieve this type of inhibition. And the other point, that the non-competitive inhibitor binds to a site other than the active site. Let's see here. Then this is our enzyme, and the substrate binds here, and then the inhibitor binds to the other site. Or the enzyme can bind the inhibitor first and then the substrate. So this is the difference. This is one of the differences between this and the competitive inhibition. So لاحظوا in non-competitive inhibition, how we identify this type of inhibition. Inhibitor does not interfere with substrate binding, so value of Vmax decreases and value of Km remains the same. And increasing substrate concentration cannot overcome non-competitive inhibition. So inhibitor and substrate are not competing for the same site because each one binds to a different site. So again, let's look. So in the presence of this non-competitive inhibitor, I, the inhibitor, maximum velocity of the reaction Vmax has the following form. So Vmax in the presence of this inhibitor equal the original Vmax divided by alpha. We call this alpha. So we can say Vmax decreases by this value called alpha. And Ki is the dissociation constant for the enzyme inhibitor complex. So again, Vmax decreases. Hey, Vmax. This is Vmax in the presence of the inhibitor equal the original divided by a number alpha, so it decreases. Whereas Vmax does not change at all. And this is the form of the Lineweaver-Burke equation. Now slope and intercept change. X-intercept remains unchanged. And here alpha is multiplied both by the slope and by the y-intercept, as you can see. Now, what is the shape of the Lineweaver-Burke plot? Again, you see this is minus I means in the absence of the inhibitor of this type. Again, we have this normal. This is the y-intercept equal. Okay, this is the y-intercept equal 1 over Vmax and the x-intercept minus 1 over Km. Now, when we add this type of inhibitor called non-competitive, so you see this line, they do not meet here at the y-axis. If we extrapolate this until the end, then they meet here. So what we conclude that Km does not change, as I said, and Vmax indeed decreases. To prove this to you, مثلا, suppose this 1 over Vmax here equal 3, and here this is equal 4. Now Vmax here is 1. If this is this is 1/3, and the new Vmax is 1/4, so it decreases from 1/3 to 1/4. This is yani. So know the shapes of all these type of inhibition in addition to seeing this example. Sucrose, common table sugar, is hydrolyzed to glucose and fructose in a classic experiment, etc. So reaction is catalyzed by enzyme called invertase. Using the following data, determined by the Lineweaver-Burke method, whether the inhibition of this reaction by 2 molar urea is competitive or non-competitive. Again, the data is given, the substrate concentration, and here velocity in the absence of the inhibitor and the new velocity in the presence of the inhibitor. You طبعا invert these upside down, and then you plot velocity versus 1 over V versus 1 over S, and then 1 over V of the inhibitor versus 1 over S on the same plot. So what you get, if you get something like this, so what type of inhibition is this? By now you know. Okay, that's why you should know So note that the two plots have different slopes and different y, typical of non-competitive. Note the same intercept of the negative x-axis, which gives -1/km. So by knowing the shapes of these plots, you can, if we give you any plot and we ask you to determine the values of both Km and Vmax from the plot, you can. Also, you can determine the type of inhibition, whether it is competitive or non-competitive. Now, there is something called mixed non-competitive inhibition. The inhibitor can bind to the enzyme at the same time as the enzyme substrates. It is similar to non-competitive, but the binding of I does affect the binding of S and vice versa. The binding of the inhibitor affects the binding of the substrate, yes. This type of inhibition can be reduced but not overcome by increasing the substrate concentration. We have dissociation constants K1 and K1 Ki and Ki pri are not identical. You see the two plots, they do not meet here or meet here. So both values change. Again, we have the two lines in the absence and in the presence of the inhibitor. They do not meet either on the y-axis or the x-axis. So both values of Vmax and Km changes. How they change? Km, as we saw in competitive inhibition, increases, and Vmax, as we saw in non-competitive, decreases. So what can you say? Whenever you heard about mixed inhibition, this is a combination of competitive and non-competitive. It is a combination of the two. This is non-competitive. Also, we have another type called uncompetitive inhibition, where inhibitor can bind to the ES complex but not to the free enzyme. Then here, this is the first difference. This inhibitor binds only to the bound enzyme. We saw in competitive, it binds to the free enzyme. In non-competitive, it binds the free enzyme or the bound enzyme, whereas in uncompetitive, it binds only to the bound enzyme. Now, the Lineweaver-Burke plot contains parallel lines, which means again that both values changes, which means that both values decreases. Even two parallel lines. So you have now three common types of reversible inhibition: competitive, non-competitive, uncompetitive. So in the uncompetitive, Vmax decreases. This is -I in the absence, and this is in the presence of this type of inhibition. Vmax decreases and Km decreases. So this is called uncompetitive inhibition. So distinguish between these all types of inhibitors. We might bring you a plot, and this plot, we ask you to determine the value of Km and Vmax and the type of inhibition. And then what happens for the values of Km and Vmax? I mean decrease, increase, no change, etc. Now the last slide here and the last type of inhibition is called irreversible inhibition. Now, in this type of inhibition, covalent binding of an inhibitor to an enzyme causing permanent inactivation. Even whenever a covalent bond is formed between the enzyme and the inhibitor, then this will lead to inactivation. على طول, permanent. That's why they are called sometimes suicide inhibitors. Even irreversible inhibitors, sometimes called suicide inhibitors, and these are molecules used to bind to an enzyme irreversibly and inactivate it. Also called Trojan horse substrates. And they are used in medicine, and there is the example is in the antibiotic called penicillin. Penicillin acts in this way. Even they are often used in medicine, and in the case with the antibiotic penicillin, this penicillin binds to a specific serine residue of a necessary bacterial enzyme, rendering the bacteria unable to make their cell walls. So you see how the mechanism. Then, in the case of antibiotic penicillin, how it works, يعني it binds to a specific serine residue, يعني amino acid serine residue, at which is necessary for bacterial enzyme, and this making the enzyme bacteria unable to make their cell walls, and they will die. Okay, by this we conclude this chapter, ladies and gentlemen. Thank you for the participants. اللي كان عددهم بعدد الأصابع اليد أو أقل. بس احنا we should finish this, and we finish this chapter. And next week, remember the exam, the test, which will be held on the date you know, on Sunday. Good luck in your test. 10 questions with 10 grades. Okay, thank you and goodbye.